Hello, good afternoon in Asia, good evening in American continent, and good evening in Europe. The current speaker is Kenta Nakajima. I belong to Technology Research Association of Secure IoT Edge application based on RISC-V architecture, TRASIO. TRASIO is a non-profit organization and runs a Japanese national project. The second author is Kuniyasu Suzaki. He is a researcher of TRASIO and National Institute of Advanced Industrial Science and Technology, AIST. Here we will talk about security on RISC-V. The title of our presentation is Portable Implementation of Global Platform API for TEE. This slide shows today's contents. Firstly, we introduce TEE, Trusted Execution Environment. TEE is a new security extension on current CPU. TEE is independent of normal OS and can run a critical application. However, we cannot use POSIX API Linux system call, so we must write a special program for TEE. We can use SDKs for TEE programming, but these SDKs depend on CPU architecture and there is no compatibility. Among them, GlobalPlatform GPAPI is the most popular API for TEE, so we implement it on RISC-V. And we introduced the implementation difficulty and CPU architecture dependent API and CPU architecture independent API on crypto library. And we also measure the performance of each GP API and report it. Finally, we summarize conclusion and the next step. First of all, we introduce TEE. Current OS has many vulnerabilities and critical applications are involved. This type of application is desired to be run independently from the OS. In order to solve this problem, current CPU offers TEE. TEE is Trusted Execution Environment, which is isolated from the normal OS. The isolated environment is named Secure World or Enclave. The below image shows the relationship between the secure world and the normal world. Popular CPU has TEE, for example, Intel SGX, AMD SiFive, and ARM TrustZone. So this is RISC-V Global Forum, and you are also interested in RISC-V. Does RISC-V have TEE? RISC-V is open architecture, and it has some implementations of TEE. For example, Multidome is Hex5's product and others are academic projects. Sanctum is developed by MIT and presented at Usenix Security 2016. Timber 5 is developed by Graz University of Technology NDSS, presented at NDSS 2019. MI6 is developed by MIT and presented at Micro 2019. Keystone is developed by UC Berkeley and presented at Eurosys 2020. All of them are very innovative. Among them, we chose Keystone because it is open source project and now it's active. What is Keystone? This slide shows the overall images of Keystone. The left figure shows the RISC-V boot procedure and TEE creation. The right figure shows PMP. PMP is Physical Memory Protection Register. To separate physical memory for each enclave, PMP is managed by 8 to 16 registers, which indicates memory region permission. After the power on, the highest privilege enclave PMP0 is used. This enclave is used by Secure Monitor Parametry. Secure Monitor manages the creation of other enclaves. After that, the lower image PNPN is created assigned to Linux. This enclave is normal world. Other PNP is used for enclave or secure world. The secure enclave is created dynamically by the request of Linux application. The memory for the secure enclave is allocated from the Linux. The secure enclave runs a trusted application with runtime called LEOS, which works as a trusted OS. This left figure shows two trusted applications are created. When a trusted enclave terminates, the memory is returned to the Linux. TEE is independent from the normal OS and there are no POSIX API. So how to write a critical program for TEE? In fact, each CPU architecture offers each SDK to program a trusted application easily. On the other hand, some vendors offer specific SDK. For example, Intel SGX has Intel Original SDK. Microsoft offers OpenEnclave. OpenEnclave is designed to run Intel SGX and ARM TrustZone. Google offers Asilo, which runs on Intel SGX and AMD SiFive. Red Hat offers Linux on AMD SiFive. GlobalPlatform GPT internal API is used on ARM Cortex-A. Unfortunately, each SDK does not have compatibility. Among them, only GPT internal API is designed not only for TrustZone, but also for general CPU architectures. Why do we use GPAPI? Because GPAPI internal API is popular in smartphones and many trusted OSs on ARM Cortex and follow. TrustMix Kinibi supports the API and runs on over 1.7 billion devices. QSEE is a Qualcomm trusted OS and runs on more than 60% of Android phones. Opti is open source implementation maintained by Linaro and used many researchers. Our group have developed some trusted applications, TAs, on Opti and want to run them on RISC-V Keystone. What is GPT internal API? The GPT internal API is different from normal POSIX API because it defines a category name or cryptographic function but does not fix a cipher suit. The cipher suit is defined by arguments in each TAPI internal API. Here's an example below. The API starts from TE and above, and the same shows category only. The main function cipher suit is defined by the arguments. This sample program below shows the SHA-256 hash. This slide shows the specification of GPT internal API. It summarizes the category and function name. It includes 29 categories and 131 functions. The cipher suit is assigned by arguments, and the specification lists up the algorithms. The left table shows the default algorithms, and the right table shows the option algorithm. So far, we introduced the definition of TEE, RISC-V Keystone, and GlobalPlatform GPT internal API. From now on, we are going to present what we did on RISC-V. We designed the GPT internal API library to be portable, So we implement it on RISC-V. We use existing Keystone SDK because we use the Keystone runtime LEOS. To implement it, there are some implementation challenges. There are 3 implementation challenges. The first one is the combination of GP internal API and the Cipher suite is numerous, so we pick up some important GP internal APIs. The second challenge is that some APIs depend on CPU architecture. We separate APIs into CPU architecture dependent and independent on crypto library, so we should implement it properly. The third challenge is to integrate GPT internal API to Keystone SDK. Keystone SDK includes EDL library. EDL is enclave definition language, and in Keystone, it is named Keyedger. Keyedger creates the code for OCO to check the pointer and boundary. OCO is request from T to REE to need help for Linux. The library must take care of it. We separate GPT internal API into CPU architecture dependent and independent. This table below summarizes the categories and functions. CPU architecture dependent categories are random generator time, secure storage, and T-generic key in transient object. T-generic key function in transient object needs random number. On the other hand, CPU architecture independent categories are crypto-common, authenticated function, encryption, symmetric, asymmetric cipher, message digest, and transient object except T-generic key function. Some categories have dependency on crypto library. CPU architecture dependent categories have no dependency on crypto, but CPU independent categories does. The most global one is crypto common because Cipher suite must be registered to the crypto common before use. Transient object is next because the space for encryption key must be prepared before use. This sample program shows the example. The sample program is categorized by each function. A rectangle indicates transient object. Blue rectangle indicates transient object. Orange rectangle indicates crypto common, and black rectangle indicates asymmetric cipher. CPU-dependent APIs need help for Linux or use an architecture special implementation. This type of APIs causes requests from T to RE named OCO. For example, T generate random in random generator category, T get RE time in time category, secure storage APIs, or and transient object APIs. On the other hand, T get system type function uses RISC-V RD cycle instruction. It not use OCO. The code for OCO is generated by Edger to protect the pointer and boundary. It avoids bugs, so it's good for developers, but it causes extra overhead instead. CPU-independent APIs are crypto-related. They are implemented as a portable library. The support algorithms are AES ED25512 and SHA-256. However, the library does not support obsolete algorithms, for example, DES or SHA-1. These algorithms are offered by Cipher suite library. In current implementation, the user can select two Cipher suite library, either Wolf Crypt and embed TRS. So far, we expressed GPAPI introduction and implementation for multiple CPU architectures, namely RISC-V, Keystone, Intel CX, and ARM TrustZone. We measured the GPAPI performance to compare between the three. The slide shows the condition of performance for GPAPI. GPAPI in RISC-V, Keystone, and Intel CX are portable libraries we newly implemented, and we use Chassis OS Opti in ARM TrustZone. In RISC-V Keystone, we use SiFive Unleashed board. In Intel CX, we used Intel NUC machine, and in ARM TrustZone, Raspberry Pi 3 Model B+. So we try to make the same condition as much as possible, but in Raspberry Pi 3, CPU speed can be selected only 600 MHz or 1400 MHz, so we chose the bigger one. And in performance measurements, we use timer reinstruction for each architecture internally, so we get the results in cycles. For example, RISC-V Keystone uses RD cycle pseudo instruction, Intel SGX RD TSC instruction, and Opti uses CNT VCT EL0 register. And we need to compare the results fairly, but the timestamp frequency in each architecture is different. So we also transform from cycle counts to microseconds. The last condition is that we take 100 measurements for each condition and each API and calculate statistics. This slide shows table of performance results in each GPAPIs except for secure storage APIs. The number is the unit of clocks on the left and the microset on the right. It is because timestamp on each machine is different. Currently, RISC-V Keystone has low performance overall because the key etcher uses FlashCC. The library FlashCC is relatively heavy. Also, the table shows the T generic key function and asymmetric cipher functions are heavy. This slide shows the table performance results in secure storage APIs. Because secure storage APIs are I/O intensive, so it's necessary to show not only on average but also in standard deviation. In Keystone, the performance of T cross object depends on T write or read object data, so we bundle two functions in this table. It shows that T create persistent object and T write object data have large deviation in RISC-V Keystone and TrustZone. We guess the reason caused by both machines use SD cards for the file system. What is next? The next step to GPAPI portable implementation is to implement TEEP and to increase more APIs. TEEP is the word Trusted Environment Provisioning. This topic is proposed on the later section in RISC-V Global Forum. The latter is that we are trying to increase the number of GPAPIs if necessary. Conclusion. We expressed the brief introduction of GlobalPlatform GPT internal API and challenges in its implementation. The second is we implemented GP internal API as a portal library which can be applied on RISC-V, Keystone, and Intel SGX. Thirdly, we measured performance of GP internal APIs to analyze between the three TE architectures. So thank you all.